Welcome back to a new exercise. We continue the study of these graphs which require a conceptual understanding of the changes in position to define velocity, and as we're going to see now, the changes in velocity to understand acceleration. So let's have a look at this, but make sure that you have seen the previous video in which we relate position versus time with velocity versus time, because we're going to use exactly the same rules here. From the velocity versus time graphs, describing an object moving along the x-axis shown below, construct the corresponding acceleration versus time graphs. The exercise is given in the form of a graph in which the horizontal axis represents time and the vertical axis represents velocity in this case. I will start by drawing the axis of the graph that will represent acceleration versus time. We have the time in the horizontal axis and the acceleration now on the vertical axis. Going back to the previous video, in the same way as velocity is defined as the change in position with time, acceleration is defined as the change in velocity with time. In this case, we have no change in the velocity, it's the same all the time. That indicates that the acceleration is zero. That means that the line that will describe acceleration will look like just like this. In the previous video, I also gave you two particular features in your plot so you can construct the other one. Exactly the same questions apply here. The first question was, what is the inclination of the line? In this case, we see that this line has no inclination at all. It's completely horizontal. That means that the slope is zero. So if the slope in a v versus t graph is zero, that means that the acceleration will also be zero, which is exactly what we have here. It's also horizontal line. We have here another example. The velocity in this case is going up, is increasing with time. We can see that it's moving from zero to a non-zero value. This means that the velocity started as zero and then increased. This is an object that is speeding up, for example. So how do we find the acceleration versus time plot? Again, we use the same questions. Question number one, what is the slope? Is the slope positive, negative, or zero? In this case, we have an object that has a positive slope, so the inclination of this line is positive. As t increases, v also increases, therefore has a positive slope. Since the slope is acceleration, we have a positive acceleration. The second question was, is this line straight or curved? Since we have a straight line, that means that the acceleration will be constant. In other words, we have something like this. It is a horizontal line on this side of the plot because, first of all, it's positive, because the slope is positive. And second, since this is a straight line, this will be constant, so the acceleration does not change with time. In this example now, the velocity is going down, it's not going up. The velocity is going from a non-zero value and then is decreasing as time goes by and then it reaches zero. You can imagine, for example, a plane that touches ground and it starts slowing down on the runway and will come to complete stop. We will in fact see an example like this later. Alright, so we know that the velocity is decreasing. The slope here is negative because the line is going down. Therefore, the acceleration will be negative. That means the acceleration line will not be somewhere here, it's going to be down here. For this reason, I will have to extend my acceleration axis a little bit down so I can accommodate a negative value. Alright, so we have that part. The second question is whether or not this line is straight. Since this line is straight, we know that the acceleration will be constant, will not change with time. So it has a negative value somewhere down here, but it will remain the same along the motion, just like that. So once again, it's negative because the slope is negative, and it's constant because this line is a straight line. Here another example. This one looks quite similar to the first example because the velocity is just a horizontal line, but instead of being zero, this is a non-zero value for a constant velocity. So it's constant because we see it's completely horizontal, so it does not change its value as time passes by. This is the example of any object that moves with constant speed. This is just like the trains that we encountered a few exercises before. Alright, so how do we find the acceleration? Well, here we're going to find an interesting aspect that is going to be extremely relevant, very, very important in a future chapter. Let's answer the two questions that we use for all these exercises. First question, what is the slope of this line? We already mentioned that this is a horizontal line, therefore the slope is 0. There's no inclination. So slope equals 0 means acceleration equals 0. So our acceleration will start here. The question is, how does this evolve? Does it change? We answer that by looking at how straight this line is. Since this line is straight, the acceleration will remain constant. It's going to be the same all the time. Since it started at 0, it will remain as 0. Just like that. So notice that even though the first example here and our fourth example here are not the same velocity versus time graph, their corresponding acceleration versus time graphs are identical. So there is something about an object at rest compared to an object that is moving with a constant speed. Actually, you can put it the other way around. You can in fact say that an object at rest is just a particular case of an object moving with constant speed, which is true. Now, this is going to be extremely important, as I mentioned, because in the future we're going to need to find acceleration, and sometimes that information is not given. We're usually told the object is moving at a constant speed, or the object is at rest. So from there, we immediately should be able to identify that the acceleration is 0, just as we did here. Here we have another example. Just as in the previous exercise, we have this kind of motion that involves several segments, so I would like to identify each of them individually. There you go. And once again, we go segment by segment. In the first segment, we have this line here. Velocity is increasing with time. That means positive slope, which in turn means positive acceleration. So acceleration will be somewhere here, it will not be down here. So it's a positive slope. Second question, how straight is this line? Well, we have a completely straight line. That means that the acceleration will be constant. That means that our acceleration will be somewhere here, just like this. Horizontal line, that means constant acceleration, and positive because the velocity is increasing. In the second segment, we have a line that is going down. This is a negative slope. The inclination is going down, which will represent a negative acceleration. In addition to that, the fact that this is a completely straight line tells us that the acceleration is constant. So it's negative and it will not change with time. If we now look at the amount of inclination, that means how inclined this is compared to this, if you want the steepness of this line, is a little bit lower than the steepness of the first segment. This means that the magnitude of this acceleration is lower than the initial part. So our acceleration is negative because it's negative slope and it's constant, but the magnitude has to be a little bit lower than the magnitude of the previous acceleration, which translates on a line that is closer to the axis. So this amount here is lower than the amount we had before. Okay, third segment. We have a completely horizontal line, so the object is moving with constant speed. That means 0 acceleration. The fact that it's a straight line again tells us that this is a constant acceleration, so it will not change with time. Finally, we have a very steep decrease in velocity, in fact, all the way down to 0. This slope is negative, the line is going down, therefore the acceleration will be negative. But what is more important is the steepness of this line. It's way steeper than any of the two before, so the magnitude of the acceleration will be larger than any of the two before. Since this is a straight line, the acceleration will be constant, so I can do this just like this. I want to stress how far this line is from the axis compared to the other two cases. So this tells me that the acceleration in this segment is negative, is constant, and is quite high because of the steepness of the line over here. Okay, let's see one final example. In this final case, we also have several segments that I would like to distinguish. So once again, I will put my dashed lines, just like that. Let's look at the first segment. We have an object that starts moving with some velocity, and this velocity decreases to another value. This means that the slope is negative, therefore the acceleration will be negative. We know the acceleration will not be up here, will not be above the axis, will be down, somewhere down here. Second feature, the line is completely straight. That means that the acceleration will be constant. The line is not very steep, it's going down but it's not very steep. Our acceleration would look like this for the first segment. Negative, constant. Great, let's move on. After reaching that velocity, the object continues moving for some time, keeping that velocity constant. Since acceleration means change of velocity, if the velocity doesn't change, then there is no acceleration at all. So the acceleration will be 0. Again, since the line is straight, the acceleration will be constant. So the same value will be maintained in all these segments. Third segment, the object suddenly starts speeding up quite steeply. So this tells us first that the acceleration is positive because we have a positive slope. Second, we have a straight line in the v versus t graph. Therefore, we have a constant acceleration. So our acceleration will be on this part, will not be below the axis. And the fact that this line is quite steep means that the value of the acceleration, that means the magnitude, will be quite high. So I will draw it like this to make clear how large this quantity is compared to this quantity we had in the first segment. Finally, in the third segment, we have that the object reaches some velocity and it keeps moving with the same velocity. So it remains with constant velocity, horizontal line, meaning 0 slope, meaning 0 acceleration. Since it is also a straight line, the acceleration will not change. So we have a 0 acceleration in the last part of the motion. And that's it. This is how we solve these exercises. You can see it's exactly the same recipe followed in the previous exercise when we had position versus time and we had to construct the velocity versus time. Here is exactly the same technique. Sorry if you found this a little bit redundant compared to the previous one, but I wanted to make sure that you have seen it because, as I mentioned at the beginning of the previous video, the fact that this kind of exercises involves no numbers, so there is no need of a calculator, makes them not very common in practices. But I've seen this many times appear in exams, so make sure that you have this part clear. In the next exercise, we move back to problems involving calculations. This time, when the velocity is not constant, so we're going to have acceleration, which corresponds to the second topic of this chapter. So I hope to see you there.